Okay, we are now at section 7.9, energy diagrams and equilibrium of a system. Uh, so the motion of a system is understood qualitatively through graphs of its potential energy versus position of a member of the system. Consider the potential energy function for the block spring system given by spring potential energy equals 1/2 kx squared, as shown in the figure. The x is equal to the position of the block, and the x component of force is equal to the negative of the slope of the u versus x curve. When the block is placed at rest at equilibrium, the position of the spring, x equals 0, f of s is equal to 0. In other words, if you don't compress or stretch the spring, then the force is equal to 0. The spring force is equal to 0. Remember, spring force is equal to minus kx. So if x is 0, then the force is 0. It will remain there unless some external force acts on it. If an external force stretches the spring from the equilibrium position, then the x is positive, and the slope du dx is positive. The force Fs, the spring force, the restoring force exerted by the spring is negative, and the block accelerates back towards x equals 0 when released. If the external force compresses the spring, then x is negative, and the slope is negative. So the spring force, the restoring force, is positive, and the mass accelerates towards x equals 0 upon release. So x equals 0 is the position for a block spring system. It is one of stable equilibrium. At x equals 0, it's stable equilibrium. It says there in the sentence, x equals 0, the position for a block spring system is stable equilibrium. You can think of it as if you think of a bowl, and if you were to have a marble and let the marble go on the side, it would just roll back and forth until it settles down to the bottom of the bowl. So that's one way to think of it. It's the lowest energy state. In general, the configurations of systems in stable equilibrium correspond to those for which the potential energy of the system is a minimum. And again, the example is a ball rolling about in the bottom of the bowl. Anytime a ball is displaced from the lowest position, it tends to return to the position when released. Okay, now let's look at the next unstable. That was a stable equilibrium. This is a stable equilibrium. This is an unstable equilibrium. And we consider a particle moving. Now imagine taking that same rounded bowl and inverting it and putting if you could balance the ball right at the top of that bowl, any little agitation and the ball would roll off. So we consider a particle moving along the x-axis under the influence of a conservative force, Fx, and the u versus x curve in the figure shown. F of x equals 0. If f of x equals 0, then x equals 0. The particle is in equilibrium at this point. But this position is an unstable equilibrium. Suppose the particle is displaced to the right, x positive, x greater than 0. Because the slope is negative for x greater than 0, f of x equals minus du dx is positive, and the particle accelerates away from x equals 0. If the particle at x equals 0, if it's at x equals 0 and it's displaced to the left, that is x less than 0, then the force is negative because the slope is positive for x less than 0. The particle again accelerates away from the equilibrium position. So the position at x equals 0 is an unstable equilibrium. For any displacement from this point, the force pushes the particle farther away from the equilibrium position and toward the position of lower potential energy. The example they give is the pencil balanced on its point. If the pencil were displaced slightly from absolutely vertical position, and then release, it will surely fall over. In general, the configuration of the system is unstable, and it corresponds to those for which the potential energy for the system has a maximum. Neutral equilibrium is when the potential energy is constant over some region. Small displacements of an object from a position in this region produce neither restoring nor disrupting forces. So you could think of a ball laying on a flat horizontal surface. Now here's an example, rather complicated an example, and there's an error in the text. I'll point it out when we get to it. Okay, let's read this. The potential energy associated with the force between two neutral atoms in a molecule can be modeled by the Lennard-Jones potential energy function. Potential energy of R is equal to 4 epsilon times sigma over R to the 12th power minus sigma over R to the 6th power, where R is the separation of the atoms. The function mu sub R, not mu, U sub R, the potential energy, contains two parameters, sigma and epsilon, that are determined from experiments. Sample values for the interaction between two atoms in a molecule are sigma equals 2.63 nanometers and epsilon equals 1.51 times 10 to the minus 22 joules. It says using a spreadsheet or similar tool, graph this function and find the most likely distance between the two atoms. Well, let's just go on to the next. Okay, so, well, let me go back. We identify the two atoms in the molecule as a system. Based on our understanding that stable molecules exist, we expect to find stable equilibrium when the two atoms are separated by some equilibrium distance. Because a potential energy function exists, we categorize the force between the atoms as conservative. For a conservative force, F sub R is equal to minus du dr, describes the relationship between the force and the potential energy function. So let's look at that. Du of R dr is equal to 4 epsilon d dr of this bracket, sigma over R to the 12th power minus sigma over R to the 6th power. And if you carry out the derivation, you get, there's actually, this is where there's an error, it's 4 epsilon minus 12 sigma to the 12th over R13 plus 6 sigma to the 6th over R to the 7th. Now, so the stable equilibrium exists for a separation distance at which the potential energy of the system of the two atoms is a minimum. So we take the derivative of the function, we got that, there is a 12 missing on the first sigma, minus 12 sigma to the 12th power. We minimize the function UR by setting its derivative equal to 0. That's what we do here. Again, it's 4 epsilon times minus 12 sigma to the 12th over R equilibrium to the 13th plus 6 sigma to the 6th, R equilibrium to the 7th equals 0. We set that equal to 0, and we get the equilibrium, R equilibrium is 2 to the 1/6 power times sigma. Okay. And now if we evaluate that by putting in the R, the equilibrium position is equal to 2 to the 6th power, 2 to the 1/6 power times 2.63 nanometers, and that's equal to 2.95 times 10 to the minus 10 meters. Okay, and this is the graph of that. Let's see, it's 10 to the minus 10 meters, 2.95, right before the 3. We graph the Lennard-Jones function on both sides of this critical value to create our energy diagram as shown. Notice that the potential energy as a function of R is extremely large when the atoms are very close together. There's a minimum when the atoms are at their critical separation. That's our equilibrium position. And then increases again as the atoms move apart. When the potential energy R is a minimum, the atoms are in stable equilibrium, indicating that the most likely separation between them occurs at this point. All right, this completes our discussion of chapter 7. And we'll close it here.